solve this problem because amorphous solid dispersion is one of the most promising strategies to improve the oral bioavailability of poorly water-soluble drugs. So according to these problems, I have two main objectives in my research. First one is to formulate the amorphous solid dispersion containing ritonavir, and the next one is to evaluate the impact of different polymers on the physical-chemical properties of the system. The next part is materials and method. So for the formulation method, first some surveys were done to select the organic solvents and polymer. Then the film casting and solvent evaporation was chosen to prepare the ASD. So here is the process of to prepare the ASD sample. First, we dissolve the ritonavir into the solvent, then put the polymer in the mixture. Mix it until it becomes a clear and homogeneous solution. Then we spread the solution as a thin layer on the glass plate. Evaporate the solvent by the warm air from 40 to 45 Celsius. Then dry it at 55 Celsius for 6 hours and collect the sample, grind it into powder or granule. After preparing the samples, we started to conduct some tests to assess the characteristic of the solid dispersion system. And optical microscopy, differential scanning calorimetry, and X-ray diffraction was used to define the crystallinity characteristic. And FTIR was used to see the functional group interaction between polymer and ritonavir. So dissolution and intrinsic dissolution test was performed using the dissolution apparatus, and dissolution diffusion evaluation was performed using the side-by-side diffusion at a set rotation speed in phosphate buffer pH 6.8 with or without the surfactant between 80 maintained at 37 Celsius. And at predetermined time intervals, the samples were withdrawn, filtered, and then analyzed using HPLC to quantify the amount of drug dissolved over time. HPLC system was validated for system suitability, specificity, and linearity. The next part is result and discussion. So the experiment was conducted to select the suitable solvent which can dissolve the drug effectively. So as we see, ritonavir is freely soluble in ethanol 96% and methanol. So we chose ethanol 96% because it is environmentally friendly and affordable price. Apparent solubility determination of the drug was carried out using light extinction, and the measurement results were presented as a line graph to determine the crown point of the solution, and the assay was conducted at 350 nanometer, a wavelength that the drug itself does not observe. And as the solution begins to precipitate, light scattering increases, leading to a sharp rise in the absorbance. So this inflection point is referred to the crown point, marking the onset of visible turbidity. According to the reference, the solubility of crystalline ritonavir in buffer phosphate pH 6.8 is 4.45 microgram per milliliters, much lower than the apparent solubility in the table. So which proving that the polymer has an ability to maintain the form-4 state of drug and prevent recrystallization. And there are some sample codes investigated in my research. For 7 different polymers, we prepared the samples at 50% drug loading. And for polymer PBPBA, samples were prepared from 10 to 50%. Presented here are the results of analytical measurements used to evaluate the crystal characteristic of ASD samples. The DSC thermogram of the drug exhibited a sharp endorphinic peak at approximately 125 Celsius, indicating that the raw material was in the crystalline form. On the pattern of all polymer samples, there is no endorphinic peak, and we also see that the increase in the glass transition temperature, which proving that the solid dispersion process successfully converted the crystalline form into the amorphous form. However, the microscopic images revealed that while some samples show no visible crystal structure, there are still some samples see that we have crystal formation, such as the PL50 and E100. So therefore, the XRD results serve as a more reliable confirmation of crystallinity. So during the DSC analysis, the thermal input can cause the partial dissolution of the drug, so potentially leading to the misinterpretation. Then, XRD measurement preserves the original solid state of the sample, offering the higher accuracy in detecting rich crystallinity. So the XRD results here of the PL10, PL20, AS, and L155 sample exhibit no sharp peaks, so proving that there is no crystal in these samples. But the PL50 and E100 samples still exhibited the diffraction peaks, indicating the presence of crystalline phases. These results are similar with the microscopy results. So the molecular interaction is very important in solid dispersion, especially the amorphous solid dispersion. So it helps improve the physical stability as well as the dissolution behavior, because molecular interactions reduce the mobility of drug molecular, and upon polymer dissolution, the drug is simultaneously released into the medium through a co-dissolution mechanism. So in the FTIR spectrum of polymer HPNCAS, HPNCP, and already L155, the absorption signal corresponding to the amino and hydroxyl groups are almost completely absent. And this suggests the interaction between the amino and hydroxyl group of the ritonavir and the carboxyl group of polymers. And the graph illustrates the dissolution behavior of different drug formulations, particularly highlighting the spring and spring parachute phenomena, often observed in the amorphous solid dispersion. So the spring refers to the rapid initial increase in drug concentration, but unstable, leading to recrystallization and a sharp decrease in the concentration. The parachute describes the system ability to maintain supersaturation over time, typically due to the presence of polymer or excipients that inhibit the recrystallization. So in the graph of dissolution rate of ritonavir from ASD in non-sync condition, we see the spring effect in the line graph of E100 and L1 and P55 samples, witness a sharp increase in the first 5 minutes and then maintain the supersaturation state. The spring effects also happen in the L100 and L155 samples, but at the lower rate. This can be explained that the dissolution behavior was controlled by the carrier, showed that the slower dissolution rate. The drug control might be seen in the PL50 and AS samples, while the solubility of the drug can hardly reach the supersaturated state. This observation indicates that the polymer plays an important role in sustaining the saturation levels and improving the solubility of the API. Initial dissolution testing was conducted. However, when you see the pictures here, you can see that the particle size of solid dispersion system is 0.2 to 0.8 milliliters, much bigger than that of the raw materials. So to eliminate the influence of surface area and isolate the effects of formulation, intrinsic dissolution testing was subsequently performed, and the tablet was placed in a sample holder module, like the picture, that only one circular phase was exposed to the dissolution medium, and thereby eliminating the influence of surface area variability. So E100 showed the highest performance. P55 and L155 also demonstrated good efficiency, but in contrast, PL50 and AS consistently exhibited lowest solubility. And drug absorption from a dosage form usually has two phases, namely dissolution and permeation. So that to further elucidate the effect of karyotype on drug solubility, the dissolution diffusion test was performed using the side-by-side diffusion. This experiment accurately resembled the intestinal absorption, why only molecular in free form can diffuse through the membrane. Compared to the conventional dissolution testing, this method differentiates the bioavailable fraction of the drug, eliminating the influence of carriers, micelles, and large undiffusible particles. Back to the graph, E100 exhibit a superior dissolution efficiency, likely due to the high solubility of the polymer and the drop in pH 1.2. Under both testing conditions, we see that the L155 formulation still demonstrates high diffusion performance, while PL50 and AS exhibited lower diffusion rates compared to the raw ritonavir. So the last part is conclusion and perspective. Through this experiment, I have some conclusion in my research. First, the effect of polymers on the appearance solubility of ritonavir was evaluated. HPMCAS and coprophyll showed the greatest enhancement, increasing solubility of the crystalline ritonavir, and successfully prepared ASD formulation with 50% ritonavir using the film casting and solvent evaporation method. We investigated the influence of polymer on ritonavir dissolution from ASD using various techniques. First, sink and non-sink dissolution test. Next is intrinsic dissolution. And lastly is sequential dissolution diffusion testing. And the best dissolution performance in pH 6.8 was observed with HPMC P55 and erratic L155. And for the last, I have some perspective of my research. First is select and optimize the polymer carriers for the formulation of the ASD. Evaluate the factors affecting the stability of ASD formulation, and investigate the integration of ritonavir containing ASD into the final dosage form for pharmaceutical product development. And thank you for listening.